Hi, in this video, let us talk about exponential functions. This is going to be the goal for our chapter, is to talk about exponential functions, and we'll also learn about logarithms as a way to solve exponential functions and equations, but also log functions and equations. So there are three main questions that we'll try to answer. Is exponential functions, what are they? Let's try to remember what distinguishes them from polynomials or rational functions that we studied so far, especially polynomials, which sort of look a little similar, but we'll see what the key differences are. What are their graphs? And equations we'll pick up a little bit later in the chapter. So you may have start noticing that exponential functions are of this form, y equals a, which we mean by a is the constant, to the power of x. So note how the variable is now the exponent, hence the name, and the base is constant. And it has to be in this sort of notation where the base stays constant, it stays the same, and the exponent can vary. So the base, we want it to be positive, because if it's not positive, it may be some horribly discontinuous function. If you think about it, if you have odd powers or even powers with a negative base, they'll be switching between positive and negative, and we don't even know what it's going to be in between the integers. Because remember, the power doesn't have to be an integer. You can raise the base to any number pretty much. So there are some questions we ask: is y equals x squared an exponential function? Would it be of this form? Well, the answer is no, it's not, because, well, it's looks like a polynomial, a quadratic function. It's y equals x squared. So it's the x, the base is the variable, and the exponent is constant. So it's the opposite of what we need. So it is not. What about y equals 2 to the fifth? Well, again, it's not. If you think about it carefully, 2 to the fifth is 32. This is just a constant. So the exponent is not variable, so it's not. What about y equals 1.5 to the power of x? Yes, that would be an exponential function. Okay, so now let's talk about the graphs. The exponential functions are so profoundly easy to find in real-life applications. The exponential growth is a very common growth. It's one of the fastest growths out there. We see it with population growth, bacterial growth. A little bit later, we'll see different examples of it. Sometimes you'll hear it on the news, or maybe when you're reading an article or watching a YouTube video, you'll hear about something is growing exponentially. That is referring to this type of situation. It's very easy to see it graphically. If base is greater than 1, we distinguish it to be as growth. We can compare it with, let's say, y equals 2 to the x, something very simple that we know how to graph, and we can plot some points and actually graph it. And the graphs are actually similar to y equals 2 to the x. It's actually very easy with exponentials. Once you know one of them, you pretty much know all of them. So let's take a look. So notice how I plotted some points. The first time we do this, it's okay to make a table, and a little bit later we'll use transformations like we did with quadratic functions. They're quite a bit easier to do it that way. So note how I plotted some points. -2, you have to remember the negative exponents. It's like 2 to the -2 power. We actually can put it in denominator, and it becomes 1 over 2 squared, and so it's 1/4. We'll talk about the different exponents a little bit later. What about 2 to the -1? That actually becomes 1 over 2 to the positive 1 power, which is just 1/2. And what about 0? 2 to the 0th power is 1, and pretty much everything except 0, but we're not going to worry about the base being 0. So 2 to the 0 is 1. This is one of the common y-intercepts. 2 to the 1 power is 2, and 2 squared is 4. So note, this is I plotted some points. So here's what the graph looks like. On one end, it's going to infinity very rapidly. In fact, imagine 2 to the 100 power. The calculator might actually give you an error message saying it's too big. We can't even calculate it. And that's just 100. You can imagine how quickly it can grow. Now, on the negative side, it seems to be going to 0, because negative exponents, remember, they end up in denominator and they make a smaller fraction. So we actually have a one-sided asymptote with each exponential function. It's a horizontal asymptote, y equals 0. So we do have one. And calculators in general do not show it, although some of the newer models will show it. I've learned there is actually a setting somewhere hidden in TI-84 Plus Silver Edition or something like that you can actually do this, but I haven't played with it, so I'm not sure if you can actually find out. Anyway, so here's what the graph looks like. Now note, any growth for any base greater than 1 is similar to that graph. I didn't plot any points. We do know it's going to pass through 1 because a to the 0 is pretty much 1, and it's going to have the same similar shape, as you know it, with the same asymptote. So what do we know about it? The domain is actually all real numbers, because you can literally plug in any exponent you want, positive, negative, 0, pretty much anything, including fractions and decimals. Now what about range? That's the y values. Note how it's 0. We start with the asymptote. Usually the lowest point is 0. It's with parentheses because we are not actually ever going to reach 0. 2 to the x is something positive. No matter how small, it will actually never get to 0. That's why it's an asymptote. So 0 and to positive infinity. That can vary with a shift, so the range can vary. Y-intercept is 0, 1. If you note, in this case, it does not cross x-axis, so there are no x-intercepts. And we do have a horizontal asymptote, which is y equals 0. Okay, now let's take a look at decay, which there's also a lot of examples in real life, like radioactive decay, or we can talk about population decay. Sometimes population is dying off as opposed to growing, which happens with some animal populations nowadays, and so on. So the example I'm showing is, what about 1/2 to the power of x? Or sometimes you can write it with a negative exponents. A little bit later with logarithms, we'll review all the exponent rules, so you'll get a chance to refresh that. So it's 1/2 to the power of x, or another way you can write it as 2 to the negative x. So whenever you see negative x, usually that signals decay for us. So usually the base is between 0 and 1. We don't want it to be 0 or 1 because those would not be very interesting functions, because 0 pretty much to any power is still 0, except maybe for 0 itself. And 1 to any power would just be 1. It's not very interesting. But other bases would be interesting. So note, I plotted the same points. 1/2 to the negative 2. Again, we can flip it and make it 4. 1/2 to the negative 1 becomes 2 to the power of 1, which is just 2. 1/2 to the 0 is 1. 1/2 to the 1 power is 1/2, and 1/2 squared is 1/4. So the opposite situation happens. Note how it decreases over time, and it's going to go to 0 or die off, basically. So again, same other characteristics apply, but we do have a decay here. Okay, and this is where is my note about graphing calculators. Again, depending on the model you have, it may be available, but check it out. But in either case, we can just put it by hand, and I'll show you how to do it with transformations. So let us apply what we know about shifts and so on from polynomials or quadratic functions when we did it. Same exact idea of the shifts applies in this case as well. Let's say if we want to graph or sketch a graph of y equals 2 to the power of x plus 3 minus 1. So I usually like to figure out what is being shifted. Well, it's y equals 2 to the x. This is the base model. I like to do this because I like to figure out if it's growth or decay. In this case, it's growth. Base is bigger than 1. It's shifted. Notice how 3 is together with exponents. So definitely it signals a horizontal shift, left or right. Happens to be 3 to the left. Remember, if positive, we're usually shifting in the opposite direction, to the left. And 1 down. So vertical shift is outside of the function. Definitely negative means down, positive means up, and so on. So how do we graph this? What I usually start to graph is the asymptote. I figure out where does it go from 0. If you're moving it left or right, it's like moving infinite string. It doesn't go anywhere. You can move your arrow back and forth, but it still stays right there. But it does move up or down. I did my best to make it straight, but it's actually going to move down to the negative 1 because we have 1 down shift. So it moved down and it becomes at y equals negative 1. Now, there's one point that we always know about the function. This is 0, 1. This was in the original function of y equals 2 to the x. Now, where does that point go? It's sort of like slope. We try to figure out with the shifts, where does it go? It moves 1 unit down. So now we're on the x-axis. And then we move 3 units to the left. So 1, 2, 3. So we're going to end up at -3, 0 at this point right here. So this is one point, like a reference point, where we can always shift it, figure out where it goes. And from there, I just draw the graph. We don't have to figure out x or y intercepts if we can't. Here we happen to have the x-intercept. But I basically put the general shape. On the homework, you may have to choose appropriate graph. Of course, you can use a graphing calculator, which doesn't show you the asymptote, but you can still graph it. But be careful with logarithms, you may not be able to do it. So it's good to be able to do it by hand. And also, sometimes you may not always have a graphing calculator at your disposal. Okay, let's try another one. What about y equals 4 to the -x minus 3? Okay, so you can always pause and try to see if you can graph it. I kind of give it away right here. Maybe did this too early. But you can try to figure out, well, is it growth or decay? Looks actually like decay. And in fact, if you think about it, it also signals being reflected about y-axis because it's -x. And the decay is a reflection about y-axis. If you think about it, it's symmetrical, but you will switch it, flip the graph that it's decreasing as opposed to increasing. Anyway, I kind of give it away. It's actually y equals 1/4 to the power of x. You don't have to rewrite it like that, but basically to let you know it's decay. And it's shifted 3 down. Okay, so same exact shifts apply. So what do we do 3 down? So again, to try to figure out where the asymptote goes from 0, well, it goes to -3, which is I drew it right here. And where does our reference point go? It goes from 0, 1. It goes 3 units down. So it goes 0, -1, -2. And so it's right here at the -2. We didn't have any horizontal shift, so it just stays right here. And there is your decay graph. Okay. All right, what about the next one? What if we have y equals -3 to the power of x minus 1? So whenever we have the negative on the front, in addition to the shifts, we also have reflection. So note how we have it still shifted 1 unit to the right, together with the exponent, but it's also reflected about x-axis. What I generally do with a graph like this, I drew the graph reflected about x-axis first. What if it's just -3 to the x? I basically took the original graph. Let me see if I can pause it and draw it for you. Okay, so the original graph sort of looks like this. I'm just kind of drawing it dotted line, but then if you reflect it, notice how it looks upside down and it actually goes through 0, -1. So now it's to this reflected graph that the shifts apply. So what I did is, so there was also shift 1 unit to the right, so the asymptote didn't move. Otherwise it would move as usual, but the asymptote stayed the same because there are no vertical shifts. Now, the point did go from 0, -1. It went 1 unit to the right, so now it's at 1, -1. And then I drew the rest of the graph, basically just the same shape if you know it, but just passing through this new shifted point. And that's about it. Okay. Now, I think we're done with the graph. There are a lot of applications of exponential functions. Some of the interesting ones are interest, financial, also mortgage, which sometimes you may actually see in this class. And also, well, of course, population growth, bacterial growth. Those are some of the biology ones. And then maybe later we'll see Newton's cooling law, which has to do with cooling of a pizza pan, or a little bit later maybe we'll even see a forensics problem, which is kind of interesting to calculate the time of death. So in this section, for now, since we haven't learned logarithms yet, we'll just explore simple and compound interest for now. Simple interest, here we're given an equation. It's just, well, it's simple, pretty much. I equals P times R times T. So P stands for principal, or the original amount invested. R is the rate, but usually it's given as a percentage, but you have to turn it to the decimal, divided by 100. And T is usually time in years. So note how it does just give you the interest. If we have to find simple interest, we're given this information. Let's say if P is $1,000, R equals 1.5%, and T is 3 years. Note how we got the R to be 0.015, and we multiply them together to get $45. So not a lot on $1,000, but still pretty good. Okay, what if we have something a little bit more complicated? What if we have the amount, but R is 4, sort of like a mixed fraction, 4 1/8, and then T is 6 years and 8 months. You should probably pause the video and try to do it without looking if you can. But I'll give you guys a hint. Once you had a chance to work this out, 1/8 you can divide. You'll get like 0.125, I believe, and then add 4 on top of that, then divide. And the 6 years and 8 months, you have to convert that to years. So you can divide 8 by 12. You'll get like 2/3 or 0.667. I kept it as a decimal that added 6 on top of that. Then I multiplied everything on top of it. So see, this is what I get. So this is what I did. I took this repeated decimal. I did not round it. I added 6 to it. Then I multiplied it by 0.04125 and 8670. And this is what I have, $2,384.25. This is pretty good. This is a good interest here. Okay, compound interest works slightly differently. It's basically, we get future amount here as opposed to the interest. We can always find interest, subtract the future amount minus the principal. So this is how it works. It's principal times 1 plus rate over the number of compoundings. That's why we call it can be compounded several times to the power of n times t, hence the exponential function. So there's different number of compoundings we can have here per year. We can have daily, which is 365, monthly, which is 12, quarterly is 4, semi-annually, which is 2, and annually, which is 1. Sometimes you see like biannually or continuously, which we'll get to shortly. Okay, so how does it work? Let's take a look at some problems. I'm not going to go through all of them. I'll just do maybe one example number 3. So once we get to it, this is continuous interest. Because there is no n is going to infinity, there is a famous limit, if you look it up, that actually approaches e. Limit is from calculus idea, that's why I'm not mentioning it here. But you get this equation, a equals p times e to the rt. I have not mentioned e yet, but it definitely is not going to be a stranger to us. This constant is going to be similar to pi. It's actually 2.718 and so on. It just keeps on going. You can actually find it on the calculator right above the ln. If you click on second and then ln, you'll get the e, basically. So the graph is similar to the growth. It is growth because it's bigger than 1. And you can use it for continuous interest. The one that was kind of interesting was about the price appreciation problem. What if we have in 2010, the median price of a house in Miami was $190,000. Assuming a rate of increase of 3% per year, what can we expect the price of such a house to be in 2015? So you can take your time to think about it, but the principal is basically 190,000. Rate is 0.03. We assume it's compounded annually because it's per year. And t equals 5 years, the difference between the 2015 and 2010. So I'm getting 220,262.07. Let's disregard the cents because it's price of a house. So that's just it's about $220,262. So still not bad. Now, occasionally, what if you know about future value, like how much you want to save to buy a car, house, etc., but how much you're wondering how much to invest, and this is called the present value. Basically, you can divide both sides by 1 plus r over n to the nt, so you can actually divide by it, or you can make the exponent negative, which is what we usually do. So there's some examples of that. There's an interesting one about a mother trying to invest at the time where her son is born to provide him with nice inheritance or a trust fund, $80,000 at age of 21, and it's 7% compounded quarterly. So note how we set this up. It's 80,000 times 1 plus 0.07 divided by 4 close parentheses. Now, depending on the calculator you have, if you have like the caret sign, then put parentheses. If it shows up as exponent like this, you don't need parentheses, so you can just put -4 times 21. And make sure to use the negative with the answer sign at the very bottom. And this is what I get. It's actually not bad for 21 years, $18,629.40. And that's it on exponential functions for now.